So here's the diaphragm here. Imagine this contracting and pulling down, increasing the volume up there, but then relaxing, and that would then decrease the volume. Breathing, one of the most important life-sustaining tasks that you perform every minute of every day. So how does this amazing machine that we call the human body accomplish this task? And how much control do you really have over this task? Because I'm pretty sure up to this moment, you weren't really thinking about your breathing, but you probably are now. So we need to address this level of control that we have. Also discuss when we have increased oxygen demand that takes place during something like exercise. Even discuss how breathing is even influenced by emotions such as laughing and crying. So we've got a lot to discuss here. So take a deep breath and let's do this. So in general, we say the point of breathing is to exchange carbon dioxide and oxygen with the bloodstream. And of course, if we're going to talk about breathing, we have to talk about the organs that are in charge of that exchange, those being the lungs. So we are in the anatomy lab. Let's take a look at those in this cadaver dissection here. So what you're taking a look at here is a thoracic cavity. We've removed the chest wall and even the abdominal wall down lower. And yes, we've got some cool little lungs here and here. Now the right lung actually has 3 lobes, and if you see, there's the division right there between the superior and the middle lobe, so that's 1 and 2. And then if I reflect those away, you can see the 3rd lobe back here, and that's the inferior lobe here. The left lung only has 2 lobes. We've got the superior lobe here, and if I kind of move this big old heart out of the way, you can probably catch a glimpse of that inferior lobe there. And you can thank this big old heart for crowding out that potential 3rd lobe of the left lung. But let's talk about this whole idea of what we need to happen for air to be exchanged with the lungs and eventually get into the bloodstream. For oxygen exchange to occur and for breathing to occur for that matter, we have to increase the volume of this thoracic cavity. And we're going to do it 2 ways. We're going to increase it vertically by pulling things down, and we're going to increase it by increasing the width, essentially by bringing the ribs out and up. Now, if that happens, we can get more air into this cavity. One thing you have to really pay attention to here that's kind of important to note, these lungs on the cadaver are deflated. That would be bad if that were inside you. Obviously, this is a cadaver, but I want to bring up this key point here. Inside of you, there should be no space between the actual lung and the inside of the thoracic wall here. Now, on the inside of the thoracic wall, there's this thin membrane called the parietal pleura. Parietal just means wall, pleura just means lung. If you come to the zoomed in view here, you can see me pinching that thin membrane right along here. Now, that membrane is continuous onto the actual lung tissue. And the membrane on the lung tissue, even though it is continuous with the parietal pleura, we changed the name to visceral pleura. Visceral just means organ, because it makes sense, it's on the actual organ of the lung. So again, to really illustrate this point, inside of you, that visceral pleura would be essentially touching the parietal pleura here. And on that zoomed in view, you could see essentially the lung tissue here, which would be the visceral pleura on top of the lung tissue, would be touching that parietal pleura, that serous membrane there, with a little bit of fluid in between. Now that fluid's super cool for 2 reasons. One, that fluid allows some nice loosey-goosey sliding and gliding between the 2 membranes to reduce friction between the actual lung and the thoracic wall. And it does something else that's really cool. Have you ever put 2 pieces of glass together, like with a little bit of water in between, and stuck them together? And I say stuck them together because when you put 2 pieces of glass together with a little water in between, it kind of sticks them together because of the increased surface tension, but it still allows them to slide and glide. That happens inside your thoracic cavity. Essentially, that fluid between the lung here and the wall here reduces the friction, but keeps the lung adherent to the wall as the chest wall expands during deep breathing and even regular breathing. So one of the things that I found really helpful when learning about the mechanics of breathing was breaking it down into kind of these 2 separate phases of breathing in versus breathing out, or inspiration, inhalation, expiration, exhalation. So let's start with the muscles that are involved in inspiration, or in other words, breathing in. And we're going to start with the diaphragm. And if you take a look at the cadaver dissection, you can see the diaphragm here. Now, one thing to note about the diaphragm is it is a divider. Essentially, it divides the thoracic cavity above from the abdominal cavity below. But when these muscle fibers here contract, the whole diaphragm will pull downward and therefore increase the vertical volume or vertical size of the thoracic cavity. Now, relaxed diaphragm's kind of more bulbous or kind of pushed up in the middle, but contracts and pulls downward. Now, during relaxed, kind of quiet, normal breathing, the diaphragm will move about 1 centimeter. But during active breathing or really forced breathing during exercise, can move up to 10 centimeters. For all you non-metric people, that's about a little less than a ½ inch, all the way up to 4 inches from that variability from quiet breathing to breathing during exercise. Now, that's not the only muscle involved with breathing in. There's some other muscles between the ribs that we need to talk about. Let's use Jeffrey for an example here. So Jeffrey has these things called ribs here. The fancy pants name for ribs in anatomy is costal. So these costals have spaces in between, and they are called intercostal spaces. Crazy, the muscles that occupy those spaces are called intercostal muscles. And there's one that we really need to talk about for breathing in, and that is the external intercostal. If you take a look closely here, you can see a rib here and some muscle fibers in between. These are the external intercostal muscles, and these muscles help to elevate the ribs, and they have that specific fiber orientation of pointing down and inward. Now, we still have some other muscles. We've got diaphragm, we've got external intercostals, and we have some other muscles like this muscle here that I'm trying to get to bulge out of my neck here. This muscle here is called the sternocleidomastoid because it attaches from the sternum and the clavicle, sternocleido. Mastoid is this bump on the back of your skull right behind your ear, but it's not as cool on me. Let's show you on the cadaver. So here is the sternocleidomastoid. And we have obviously cut the clavicle here so you can't see its clavicular attachment here, but this is the sternal attachment, and when this contracts, it would help elevate the sternum. And when I reflect this, it will also expose some other breathing muscles called the scalenes. Now, if we look closely, you can see this cool little nerve bundle right here. But there's 3 scalenes. There's an anterior scalene right here, and a middle scalene here, and a posterior scalene here. Now, these 3 scalenes, if you look closely, are attaching down to ribs, and I can feel the ribs underneath here and right there. Basically the first 2 ribs, because again, when we're talking about breathing, the ribs are going to be involved. So diaphragm, external intercostals, sternocleidomastoid, and now the scalenes. And one more we have to talk about, which is the cute little pec minor. So the pec minor is this muscle here, and what you're not able to see is its attachment onto the anterior rib cage that we had right here. But this attachment, or the origin of this muscle, would attach to ribs 4 and 5. Ribs 3, 4, and 5. Now, how I used to teach this to my students is we would be like this in class, and because this would be the orientation of the pec minor, ribs 3, 4, and 5, to help them remember that with their 3rd, 4th, and 5th finger. I cannot tell you how many times I would be driving into the parking lot before school, and my students would give me the pec minor gang sign. I would be driving by and they would give me this. I know. At least they learned something, right? But all of these muscles had something in common, is they attached to the rib cage. Even the diaphragm here, we had to cut it away from its attachments on the rib cage. Now the diaphragm really had this kind of vertical motion that was pulling downward, but those other muscles that we all talked about, again, I'm repeating myself, external intercostals, scalenes, sternocleidomastoid, and pec minor, all attached to the ribs. Now let's really talk about this rib thing here. Elevating the ribs occurs during inhalation or breathing in. And it's not just this little vertical motion here. You guys know when you really breathe in, you kind of feel like you get this out and upward motion. And if we look at Jeffrey again here, the ribs don't just go straight across like so. They kind of have this swooping down motion that comes down and back up to the sternum. And to really illustrate how that works, we've got the bucket analogy. And you think of this handle essentially like kind of the shape of the ribs coming down and up. Imagine the bucket itself is the lung. Now what happens if I raise this bucket handle? You can see there's that space between there, and in real life, if this were the lung, that would stay adhered to the actual rib and therefore create that volume and expansion. This is one of the coolest things that one of my professors showed me, and I finally was like, oh yeah, I can understand this whole expansion of the rib cage and how air could get into there. Something also really cool to talk about here. Remember the diaphragm, how it separated the thoracic cavity from the abdominal cavity. What's going on here is we are pulling the diaphragm down, elevating and kind of expanding the rib cage here, and that is decreasing the pressure inside, because what happens is when you increase the volume, that decreases the pressure. And what happens now is we've got all this air outside based on atmospheric pressure, and when you increase the volume of the space and the pressure goes down, what has to happen? The pressure is greater outside of your body than it is in your thoracic cavity, and so air rushes in. I always think this is kind of funny when we always talk about the lungs or these organs that are in charge of breathing. In a way, they're kind of just sitting there. They're kind of little greedy, little lazy organs where all the surrounding musculature are doing all the work for them, so then the air just rushes in and fills and expands and stretches those lungs. And one more plug for those respiratory muscles. Not only are they increasing the volume of the thoracic cavity so the lungs can inflate and expand with air, they're also having an effect on the abdominal cavity. As the diaphragm contracts and pulls downward, that is increasing the pressure of this cavity while simultaneously decreasing the pressure of the cavity above. Now, why do I care about that? Well, there are a whole bunch of blood vessels in the abdominal cavity that are draining blood from the lower limbs, the abdominal muscles, and the abdominal organs. And if I have an increase of pressure in here where all those blood vessels are and decreased pressure here, that's going to help facilitate blood flow back up to this wonderful organ that we call the heart. So not only do they help facilitate air coming into that cavity, they also help facilitate more blood flow coming back to the heart. And that can be even more important during things like exercise and deep breathing activities. And FYI, that whole process of facilitating blood flow back to the heart from the abdominal cavity is referred to as the respiratory pump. So what happens during breathing out? Well, that depends. If you're just doing normal, quiet breathing, nothing terribly exciting happens with the expiratory muscles. They don't even get involved. During normal, quiet breathing, we really just engage two muscles, the diaphragm and the external intercostals. Those other muscles of deep inspiration that we already mentioned, like the scalenes, the sternocleidomastoid, and the pec minor, again, are called accessory breathing muscles because they only get involved during deep breathing or things like exercise. But let me give you this idea or this example of just normal quiet breathing and how that affects expiration or breathing out. So here's the diaphragm here. Imagine this contracting and pulling down, increasing the volume up there, but then relaxing, and that would then decrease the volume. So contract, and then the muscle just relaxes because the muscle has this natural recoil to it. And that natural recoil helps with breathing out. The external intercostals are similar as far as contract and relax and have that natural recoil as well. So that's one component of helping you just breathe out, just by simply relaxing those two muscles. One other thing is these wonderful elastic organs that we call the lungs. Now, when you come into a cadaver lab, or if you've seen students in a cadaver lab, they're always poking and wanting to touch things. But for some reason, you always see fingers coming into the thoracic cavity and students wanting to poke these gushy, elastic lungs because they have that gushy, elastic feeling. Now, think of elastic bands. Rubber bands are great because they stretch, but more great because they snap back and recoil. Now, the recoil that's in the lungs is even greater than in the muscle tissue. So when those lungs stretch during breathing in, they naturally just want to snap back, and that's this free energy to help you breathe out during normal, quiet breathing. But when you do decide that you need to do more deep breathing, or in other words, exercise, and you need to call upon more than just the diaphragm and the external intercostals, and you bring in the sternocleidomastoid, the scalenes, and the pec minor, you're bringing that much more air into the thoracic cavity, and so it makes sense you're going to have to push more air out as well. And you're also producing more carbon dioxide, and that is when the expiratory breathing muscles are going to get involved. And of course, we're going to show you these expiratory muscles on the cadaver dissection. So let's take a look at what we nickname the chest plate for obvious reasons, because we have the anterior chest wall here. Now, the majority of these muscles are actually going to be in the abdominal body wall, but there is one up here that we really need to talk about. Let me zoom it in for you here. So right here, if you remember, this was the external intercostal going in this direction. If you look closely at the fiber orientation, there's an opposing fiber orientation that goes 90 degrees to the external intercostals. These are called the internal intercostals. Now, these internal intercostals do the opposite of what the external intercostals did. The external intercostals elevated the ribs during deep breathing, but the internal intercostals are going to pull them down to help decrease that volume and force air out. Now, the other muscles involved in expiration or breathing outward are going to be your abdominal muscles. What's really surprising to a lot of people is we typically think of this muscle here as the six-pack muscle, but this is called the rectus abdominis. I've only exposed 2 of the 6 blocks. Really, there's typically 8 on people, but we mostly nickname it the six-pack because you can see 6 more than 8 typically. And on the left side, we obviously haven't exposed that, but these muscle fibers from the rectus abdominis or the six-pack muscle go all the way up to the ribs here, and so therefore they can pull downward on the ribs, again aiding in expiration. The muscles on the lateral body wall also get involved. Here is a muscle called the external oblique. I'm going to try to lift this up so you can see it a little bit better. So here's the external oblique. What's awesome about this is if you look closely, it mirrors the image of the external intercostal, or mirrors the fiber orientation, I should say. As you can see, those fibers are going inward and downward. And that's the external oblique. The internal oblique, again, just like the external intercostal and the internal intercostal oppose each other, so do these muscles, and this one is going in and upward. So external oblique, internal oblique, and even the transversus, which is a little trickier to see, but I'm going to try to open it up for you here. The transversus abdominis also gets involved in helping you breathe out. Now, how do these lateral body wall muscles do it? Because again, they are coming up and attaching to the rib cage and therefore pulling it down during deep breathing. If you exhale hard or forcefully, you can feel the tone in your muscles. Your abdominal muscles actually do that. So go ahead and obviously do this while you're at home. Take a deep breath out and palpate those muscles. Now, one of the things we have to talk about that I mentioned in the intro is what is controlling all of this? What's going on up here in the brain, and specifically the brainstem, that's allowing us to breathe without thinking about it? And can we sometimes take over? Let's find out. So breathing is primarily controlled in the respiratory center located in the brainstem, specifically in a structure called the medulla oblongata. Now, sorry to all you Adam Sandler and Waterboy fans, but we're not going to talk about angry alligators and all them teeth and no toothbrush, but I am going to show you a real medulla oblongata right here that I'm tracing with the probe here. Now you can see this is a sagittal cut through the head. We've got the spinal cord continuing down here, and here's the vertebral column or the spine. But if we go in the reverse order of the spinal cord here, you can see the first expansion. That is the medulla oblongata. Now the medulla contains some specific neuron groups that we're going to talk about that control breathing. One specifically, if we were to zoom into the medulla right about here, we'd see a group of neurons called the dorsal respiratory group. Now the dorsal respiratory group will send signals down the spinal cord and eventually out specific spinal nerves that get the signal to the respiratory muscles. And the dorsal respiratory group specifically controls muscles of normal quiet breathing, so that diaphragm and external intercostals. Let's just give you that specific example. Dorsal respiratory group sends a signal downward, and about C3, 4, and 5, it'll exit out to send signals or neurons into this nerve called the phrenic nerve, which controls the diaphragm, and phrenic actually means diaphragm. For those of you anatomy geeks who love mnemonics, we always would say C3, 4, and 5 keep the diaphragm alive. Now that's just, again, normal quiet breathing. But there's another respiratory group right in front of the dorsal respiratory group, about right here, that would be called the ventral respiratory group. Crazy, because it's in front of the dorsal respiratory group. And that would send a signal down to get muscles involved in more forced breathing during exercise. It would send signals down through the spinal cord to, say, the muscles like the scalenes, the pectoralis minor, and the sternocleidomastoid. And then it would send separate signals, again down that spinal cord, to the muscles of expiration during deep breathing or exercise, like the obliques and the rectus abdominis. So you've got this whole center here that primarily is working automatically, so you don't have to think about it. However, all of you know that you can decide to take a deep breath. Like right now, I can take a deep breath, or I could hold my breath. So what is going on in that situation? So when you decide to control your breathing, that's because there are other centers of the brain that hook up to the respiratory centers in the medulla. One of those being the cerebral cortex, and I'm going to pull out the other half of the brain here. And the cerebral cortex has areas of conscious control that we could send signals from there down into the medulla here to regulate breathing, such as like taking a deep breath in on demand or even holding your breath. Now, why is holding your breath such an important thing to be able to do? Well, it's protective. If you were to dive into water, you want to hold your breath so you don't suck water into your respiratory tract. Or say you walk into a really bad bathroom that it would just be beneficial not to breathe in that situation. Or if there's dust particles and things of that nature. So there is this protective nature and benefit to having conscious control of your respiratory centers. Now there's some other interesting things that are kind of funny to think about. We change our breathing when we laugh, when we cry. You guys have all had that crying moment where you're like, and things like that. It's a great imitation. I'm sure you can make fun of me in the comments. But this area right here, let me make sure it's in the view of the camera here, is called the hypothalamus. The hypothalamus has some regulation of emotions, like during happiness and laughter and sadness and crying, and that can also send signals down to here to actually control this. So what we're essentially doing when we have emotional things happen or we have conscious things that are getting involved in breathing, they're relaying into those respiratory centers and changing the dynamics there as far as maybe inhibiting the breathing or activating it depending on what type of activity we're doing, if we're laughing, crying, or holding our breath.